All right, well, to start off with, we're going to look at this thing called the Bernoulli distribution. The Bernoulli family actually is a very famous mathematical family. There are lots of different Bernoullis who did all sorts of things in maths. The Bernoulli we're interested in is Jacob Bernoulli. He was a Swiss mathematician, played a large part in calculus, the discovery of calculus. He actually was on Leibniz's side in the great Newton-Leibniz argument of calculus. His big part was the discovery of the irrational number E. However, that's not what we're interested in looking at today. Today, his most famous work is to do with probability. And that's what the Bernoulli distribution has to do with. It's a simple type of discrete probability distribution, a very simple type. Simply has two possible values, 1 or 0. 1 represents success, 0 represents failure. So if we let x represent a Bernoulli random variable, and its probability density function will be this. The probability that x equals x will equal p, that's when x equals 1, when it's successful, and it'll be 1 minus p when x equals 0, when it's unsuccessful. So this is also known as a Bernoulli trial. We can also rewrite this simply as this. The probability that x equals x is 1 minus p to the power of 1 minus x, p to the power of x. Okay, let's have a look at this distribution in a little bit more detail. We'll draw up our table. As we say, there's only two possible outcomes, 0 and 1. So then in our first row, we have that the probability of 0 is 1 minus p. The probability of 1 is p. So to work out our expected value and our variance, first we need our xpx row. So we'll multiply the probability of x with x. And we need our x squared px row. That'll help us with variance. So expected value, that's the sum of the xpx. And we can see that simply adds up to p. So what we expect to happen is p. The variance, well, that's going to be the expected value of x squared minus the expected value squared. So p minus p squared. And that's where we get the p, 1 minus p. So if x is a Bernoulli distribution, and we can symbolize that with Bern, B-E-R-N, and p, the probability is what we're interested in, then we know the expected value will be p, and we know the variance will be p, 1 minus p. Well, we're actually a little bit more interested in binomial probability, where we take this idea a step further. Remember, there's only two possible outcomes, success or failure. So binomial probability is when you get a binomial experiment and you just continually repeat that Bernoulli trial. So every time there'll be success or failure. So we'll start off with, okay, the two possibilities are A or B. And let's say A is success, B is failure. So probability of A is P, probability of B is Q. But then we repeat the trial. So if we got A the first time, then we could branch out to AA and AB. If we got B the first time, it'd branch out to be BA and BB. Probability A would be P squared, AB would be PQ, BA would also be PQ, BB would be Q squared. Well, let's do it a third time. So each one of these would branch off again. There's all our possibilities. AAA, AAB, ABA, ABB, BAA, BAB, BBA and BBB. The probability of each of those, we start seeing a very familiar pattern. So PQ, P squared Q, P squared Q, PQ squared, P squared Q, PQ squared, PQ squared, and P cubed. Now, you might not see it yet, so let's do it a fourth time. If each one of those branches out. So now, AAA, AAB, I won't read them all out. We're all the way down to BBB. The probability of each of those, well, p to the power of 4, p cubed cubed, p cubed cubed, p squared, p squared q squared, and so on down to q to the power of 4. Well, let's look at it again. If it was one event, we said the probability of A was P, and the probability of B was Q. Two events, probability of AA is P squared. The probability of an A and a B, if I don't care the order, well, there was two ways of it happening. I could have got AB and I could have got BA. So the overall probability is 2PQ. Probability of BB is Q squared. Now it's really starting to look familiar. 3 events. AAA was P cubed, 2 A's and a B, and again, if I don't care about the order, the probability each time turned out to be P squared Q, and there was 3 of them, 3P squared Q. A and 2B was 3PQ squared, and BBB was Q cubed. 4 events, well, once again, we see this familiar pattern. What we've actually created is our binomial expansion, back from when we were looking at the binomial theorem. If X is a Bernoulli trial, so something that has only 2 possible outcomes, then the probability that X occurs exactly K times in N trials turns out to be the general term in a binomial expansion. So the probability that X equals K is NCK, probability of success, P to the power of K, probability of being unsuccessful to the power of N minus K. Now you'll notice I wrote it a bit strange there. I put the Q before the P, but it doesn't really matter because, of course, Q is simply 1 minus P. It's a Bernoulli trial. P, 1 minus P. Well, let's look at some examples. So we've got a bag. In our bag, there are 30 black balls, 20 white balls. We're going to pull out 7 balls, but the important thing to note about binomial probability, this is always with replacement. Okay, so it only works if it's with replacement. So we put the ball back in after we've drawn it. What's the probability of drawing all black balls? So X is going to be the number of black balls that we pull out. Probability that X equals 7 then will be 7C7. Probability of success, 3/5 to the power of 7. Probability of unsuccessful to the power of 0. So 2/5 to the power of 0. Well, that would be an exact answer there. So 7C7, 3 to the power of 7 on 5 to the power of 7. It works out to be 2,187 on 78,125. What if we're interested in 4 black balls being pulled out? Probability that X equals 4. 7C4. Probability of success, 3/5 to the power of 4. Probability of not being successful, 2/5 to the power of 3. Our exact value is 7C4, 2 cubed, 3 to the power of 4 over 5 to the power of 7. And that works out to be 4,536 over 15,625. An election. We know 30% of the voters favoured Party A. Let's say an interviewer randomly picked 5 voters as they were coming out of the polling booth or something like that. What's the probability that 3 of them favour Party A? So X is going to represent the number of people favouring Party A. Probability X equals 3, 5C3. Probability of success, 3/10 to the power of 3. Probability of not being successful, 7/10 to the power of 2. There's our exact value. Works out to be 1,323 over 10,000. Majority favour A. Majority would be 3, 4 or 5. So we'd have to work out each of those individual ones. But once again, each one is the binomial coefficient, so 5C3, then 5C4, then 5C5. Probability of success to the power of whatever you want. So the first one, 3, 4, then 5. Probability of unsuccess to 1 and 0. Notice the 2 powers always add up in this case to be 5. Let's calculate that out. There's our exact value. 4,077 over 25,000. At most, 2 of them favoured A. That's the complementary event to what we just worked out. So don't forget your probability theory. That can save time. So it'll be 1 minus the answer we just found, 20,923 over 25,000. Let's look at this HSC one from 2005. 5 matches each weekend of a football season. So Megan's going to take part in a competition. It's basically a tipping competition. She'll get 1 point if she picks more than half of the winning teams for the weekend, 0 points otherwise. Now, the probability that Megan picks a team correctly is 2/3. So we want to show that the probability that she earns a point is going to be 0.7901. Now, X is going to represent the number of matches picked correctly. And in order for Megan to earn a point, she has to pick more than half of the winning teams. So that would be 3, 4 or 5 winning teams. We need to add up each of those probabilities. Now, there's an exact value, but they've asked us to round it off, and we get 0.7901. Now go and find the probability that she earns a point every week of the 18-week season. So we're now investigating something different. So I want a new random variable. I'm going to call it y. Y is going to represent the number of weeks Megan earns a point. We want to know 18, because it's every week of the 18-week season. But we have a new probability we're talking about here, because this is the probability that Megan earns a point. So now it'll be 0.7901 to the power of 18, 0.2099 to the power of 0. But don't forget your binomial coefficient, although in this case you would have got away with it because 18C18 is just 1. But to two decimal places, we get 0.01. The third part, find the probability that Megan earns at most 16 points. At most 16. At most 16, that means y is less than or equal to 16. I don't want to work out 0, 1, 2, 3, 4, and so on. Let's do the complementary result of 1 minus the probability of y being greater than or equal to 17. And of course, one of those we've worked out already. So we'll be taking away 17 and taking away 18. And it all turns out to be 0.92. Let's try another one. 2007. So we're in a city. We know 10% of the population has green eyes. What's the probability that 2 randomly chosen people then have green eyes? So this is not a binomial probability question. This is just simply, what's the probability that 2 randomly chosen people have got green eyes? So it'll be 0.1 times 0.1, 0.01. This is where the binomial probability now comes in into part 2. What's the probability that exactly 2 of a group of 20 chosen people have green eyes? So I'm going to let X represent the number of people with green eyes. We want to know the probability that X is 2. Probability of green eyes was 0.1. So it'd be 0.1 squared. 0.9, therefore, is to the power of 18. Don't forget your binomial coefficient. So times 20C2. And we get 0.285. What's the probability that more than 2 of a group of 20 randomly chosen people have got green eyes? So once again, it's our complementary idea. More than 2 would be 1 minus the probability of less than or equal to 2. So it's 1 minus probability of 2, probability of 1, probability of 0. So each of those we work out, subtract it from 1, and we get 0.32. Okay, let's have a go at 17A.